In the summer of 1944, Londoners faced a new horror from the skies. Just 1 week after the triumphant D-Day landings, Hitler unleashed his vengeance weapons against the British capital. Pilotless aircraft screamed across the English Channel at nearly 400 miles per hour, their pulse jet engines producing an unmistakable buzzing drone that earned them the nickname doodlebugs. When that terrible sound stopped, civilians had mere seconds to find cover before 850 kilograms of high explosives detonated wherever the flying bomb happened to fall. The conventional defenses of 1940 proved woefully inadequate against this revolutionary threat. Yet within 4 weeks of a secret American technology reaching British gun batteries, the destruction rate of these terror weapons climbed from a pitiful 17% to an astonishing 79%. This is the story of the proximity fuse, one of the most closely guarded secrets of the Second World War, and the invisible burst that saved London from destruction. Let us begin with the problem that demanded such a revolutionary solution. Anti-aircraft gunnery before 1943 relied on two fundamentally flawed approaches to detonating shells near enemy aircraft. Contact fuses required a direct hit on a fast-moving target, an achievement so improbable that gunners sometimes fired thousands of rounds without scoring a single kill. The mathematics were unforgiving. An aircraft flying at 300 miles per hour covers 440 feet in a single second. An anti-aircraft shell might take 10 or 15 seconds to reach its target altitude, during which time the aircraft has traveled nearly a mile. Hitting such a target was equivalent to shooting a rifle bullet with another rifle bullet. Time fuses allowed gunners to set a mechanical timer that would detonate the shell at a predetermined moment after firing, theoretically placing the explosion in the path of an approaching aircraft. This approach demanded extraordinarily precise calculations. Gunners needed to determine the exact altitude, speed, and direction of the target, then calculate where the aircraft would be several seconds in the future when the shell arrived at that point in space. The calculations had to account for wind speed and direction at multiple altitudes, air density variations, barrel wear affecting muzzle velocity, and dozens of other variables that changed constantly. Even minor errors in any of these calculations meant the shell would explode harmlessly, either too far from the target or at entirely the wrong moment. Against the relatively slow bombers of the early war years, these limitations were frustrating but manageable. Massed batteries could create curtains of exploding steel that forced bombers to fly higher and reduced their accuracy, but the mathematics were unforgiving. Studies indicated that it took an average of 2,500 shells to bring down a single aircraft using conventional time-fused ammunition. The German V-1 flying bomb exposed the fatal weaknesses of this system with brutal clarity. The Fieseler, one of three, designated V-1 by German propaganda as Vergeltungswaffe 1, or Vengeance Weapon 1, was unlike any target anti-aircraft gunners had ever faced. Development of this weapon had begun in 1935, when Paul Schmidt and Professor Georg Hans Madelung submitted a design to the Luftwaffe for a flying bomb powered by a pulse jet engine. The resulting weapon measured 8.32 meters in length, with a wingspan of approximately 5.4 meters. Its Argus AS-014 pulse jet engine produced approximately 3,500 newtons of thrust, propelling the weapon at speeds approaching 640 kilometers per hour at altitudes between 2,000 and 3,000 feet. The pulse jet operated by drawing air into a combustion chamber through spring-loaded inlet valves, mixing it with low-octane gasoline, and igniting the mixture. The resulting explosion forced the valves shut and expelled the exhaust rearward, producing thrust. The cycle repeated 45 to 50 times per second, creating the distinctive buzzing sound that gave the weapon its various nicknames. The flying bomb carried an 850-kilogram warhead filled with amatol, a mixture of TNT and ammonium nitrate chosen for its stability and blast effect. 3 separate fuses ensured detonation on impact: an electrical impact fuse, a mechanical impact fuse, and a mechanical delayed action fuse as backup. An autopilot system using gyroscopes maintained course and altitude after launch. Air-driven vanes at the nose drove a small propeller connected to a counter mechanism that measured distance traveled. When the counter reached a preset value corresponding to the target distance, the system closed the fuel supply and operated spoilers that pitched the nose down into a steep dive. The V-1 cruised at altitudes between 600 and 900 meters, placing it in an awkward gap between the effective engagement envelopes of light and heavy anti-aircraft weapons. Light 40mm Bofors guns could traverse quickly enough to track the fast-moving targets, but lacked the range to engage them effectively at higher altitudes. Heavy 3.7-inch guns possessed the necessary range, but their traversing mechanisms could not keep pace with targets moving at such speeds at such close ranges. The rate of traverse required for a successful engagement increased dramatically as the target approached, eventually exceeding the mechanical capabilities of the gun mounts. The V-1 presented an incredibly small radar cross-section compared to manned bombers, making detection and tracking far more difficult. At just over 8 meters long and 5 meters wide, the flying bomb offered perhaps 1/10 the radar return of a medium bomber. Unlike aircraft that might take evasive action when anti-aircraft fire came close, the flying bomb maintained a steady course on autopilot, which theoretically should have made it easier to hit. In practice, this advantage was offset by the target's small size and tremendous speed. The first V-1 to strike British soil fell on Swanscombe near Gravesend at 4:18 in the morning on June 13, 1944. The attack caught defenders unprepared despite months of intelligence warnings about German secret weapons. That first missile killed 6 people at Grove Road in Bow, East London, when it struck at 4:25 in the morning. Over the following 24 hours, the attack began in earnest, with 244 flying bombs launched against London. 73 reached the capital. The attacks continued relentlessly, sometimes exceeding 100 missiles per day. At the peak of the offensive, more than 100 V-1s crossed the English coast in a single 24-hour period. Each bomb that reached its target killed an average of more than 2 people and wounded 7, while damaging approximately 400 buildings. On June 27, 1944, a V-1 struck Highbury Corner during the lunch hour, killing 26 people and injuring 150 more. 3 days later, another struck the Aldwych during lunchtime, killing 48 people and wounding over 150 in what became the third worst V-1 incident of the war. By late August, more than 6,184 Londoners had been killed and nearly 18,000 seriously injured. Over 1.5 million residents fled the city, disrupting the war economy at a critical moment in the campaign to liberate Europe. Production at factories slowed as workers failed to appear or left early for bomb shelters. The psychological effect of the constant attacks proved almost as damaging as the physical destruction. The existing anti-aircraft defences proved catastrophically inadequate. During the first weeks of the V-1 offensive, gun batteries required an average of 2,500 shells to destroy a single flying bomb. Even this dismal performance overstated the gun's effectiveness, as many of the destroyed missiles fell on populated areas, their warheads still detonating and causing casualties. Shooting down a V-1 over London merely determined where the bomb would explode, rather than preventing the explosion entirely. Britain desperately needed a technological miracle. That miracle had been under development in the United States for nearly 4 years, pursued with a level of secrecy rivaling the atomic bomb project itself. The proximity fuse, known officially as the variable time fuse or VT fuse to disguise its true nature, represented one of the most ambitious engineering challenges of the war. Admiral Lewis Strauss later wrote that the proximity fuse was one of the most original and effective military developments of the Second World War and must be listed among the very small group of developments upon which victory very largely depended. The concept was deceptively simple. Instead of relying on mechanical timers or requiring a direct hit, the fuse would contain a miniature radar transmitter and receiver that continuously broadcast radio waves. When those waves reflected off a nearby target and returned to the fuse, the increasing signal strength would trigger detonation at the optimal moment for maximum effect. The target would essentially destroy itself by its mere presence near the approaching shell. The British had been first to recognize the military potential of proximity fusing. As early as 1939, researchers at Pi Limited, under the direction of John Cockcroft, began developing thermionic valves capable of withstanding the forces generated during weapons firing. The British achieved some success with rocket-launched weapons, where acceleration forces were relatively modest compared to artillery shells. The Tizard mission of September 1940 brought British research to American shores as part of a broader exchange of military technology. Along with the cavity magnetron that would revolutionize radar, the British delegation shared their proximity fuse research. American scientists would build on this foundation to create a weapon that changed the course of the war. Executing the proximity fuse concept for artillery shells proved extraordinarily difficult. The fuse assembly had to fit inside the nose of a standard shell, leaving only a few cubic inches for all the necessary components. The nose cone of a 5-inch naval shell measured approximately 2¼ inches in diameter and 8 inches in length. Into this space, engineers had to fit a complete radio transmitter and receiver, power supply, safety mechanisms, and detonating charge. Those components needed to survive being fired from a gun, an event that subjected them to acceleration forces exceeding 20,000 times the force of gravity. A component weighing 1 ounce at rest would effectively weigh over 1,200 pounds during the fraction of a second of acceleration in the gun barrel. The shell's rotation, imparted by rifling to stabilize its flight, created centrifugal forces as the projectile spun at rates between 25,000 and 30,000 revolutions per minute. Components at the outer edge of the shell experienced forces that would tear apart any conventional electronic equipment. The fuse needed a power source capable of activating instantly upon firing and providing stable current throughout the shell's flight, which might last 20 seconds or more. Conventional dry cell batteries would deteriorate during storage, making them impractical for ammunition that might sit in a magazine for months before use. Every component had to function reliably under these extreme conditions, while remaining inexpensive enough for mass production in the millions. Given such requirements, it is small wonder that sophisticated nations gave up the proximity fuse as a technological dream beyond their research and production capabilities. On August 24, 1940, Vannevar Bush proposed and led the establishment of Section T of the National Defense Research Committee, placing it under the direction of Merle Tuve, a 39-year-old physicist at the Carnegie Institution of Washington's Department of Terrestrial Magnetism. Tuve had been born in Canton, South Dakota, on June 27, 1901, and had shown early promise in physics. He and Ernest Lawrence, who would later develop the cyclotron and play a crucial role in the Manhattan Project, had been childhood friends. After graduating from the University of Minnesota in 1922, Tuve pursued graduate work at Princeton and Johns Hopkins before joining the Carnegie Institution. His pioneering work on pulsed radio waves had helped open the way to radar development. The designation Section T stood simply for Tuve, reflecting the enormous responsibility placed on this one man's shoulders. Tuve assembled a team of brilliant scientists and engineers, including Richard Roberts, Lawrence Hafstad, and Lloyd Berkner, all from the Department of Terrestrial Magnetism. They would spend the next 2 years solving problems that many experts considered insurmountable. Within a few months, over 100 additional Section T personnel swelled the cyclotron building at the Carnegie Institution as the project grew beyond its original scope. The most critical challenge was developing vacuum tubes capable of surviving the violent forces of being fired from a gun. Conventional radio tubes used in home receivers would shatter instantly under such stress. The glass envelopes would crack, the delicate internal elements would break free from their mounts, and the hair-thin tungsten filaments would snap like cobwebs in a hurricane. Late in 1940, researchers conducted experiments with commercial vacuum tubes mounted in blocks and dropped on concrete or armor plate to test their ruggedness. The results showed a surprising degree of durability, suggesting that the problem might not be insurmountable. James Van Allen, a young physicist who would later discover the radiation belts surrounding Earth that bear his name, had joined the Department of Terrestrial Magnetism in August 1939 as a Carnegie Research Fellow. In the summer of 1940, he joined the national defense efforts with his appointment to Section T. Van Allen spent nearly a year working with the Raytheon and Western Electric companies and a Massachusetts firm that manufactured miniature tubes for hearing aids to develop tubes that could withstand artillery firing. The challenge went beyond mere strength. The tubes had to maintain their electrical characteristics precisely while being subjected to forces that would crush most materials. Van Allen experimented with new materials to cushion the glass where it seated on its metal base, preventing the shattering that destroyed conventional tubes. The team developed techniques to reinforce the fragile tungsten filaments inside the tubes, supporting them at multiple points to prevent breakage under the tremendous acceleration and centrifugal forces. Van Allen later recalled the intensity of the work during this period. As a young scientist, he was made a Montgomery County deputy sheriff so that he could legally carry a .45 automatic pistol to protect shipments of experimental fuses on their way to proving grounds for testing. The secrecy surrounding the project was absolute. By January 1942, Van Allen and his colleagues had created vacuum tubes that could survive being shot from a cannon. This achievement alone represented a major breakthrough in electronics miniaturization that would later prove essential for the space program. The National Carbon Company solved the equally vexing problem of providing electrical power. The solution was an ingenious wet cell battery that remained completely inert until the shell was fired. The battery contained a glass ampule filled with electrolyte solution surrounded by stacked metal plates. The shock of firing shattered the ampule, and centrifugal force from the spinning shell pushed the released fluid outward into contact with the plates. This instantly created a working battery that provided stable power throughout the shell's flight. The reserve battery design ensured that fuses would function reliably, regardless of how long the ammunition had been stored in magazines or warehouses. Lloyd Berkner, one of Tuve's original team members, developed a crucial improvement using separate transmitter and receiver circuits that significantly improved the fuse's sensitivity and reliability. In December 1940, Tuve invited Harry Diamond and Wilbur Hinman from the National Bureau of Standards to investigate Berkner's improved design. Within just 2 days, Diamond conceived a new fuse design using the Doppler effect of reflected radio waves. The Doppler principle, familiar from the way a train whistle changes pitch as it passes, allowed the fuse to detect not just the presence of a reflecting target but its relative motion. This approach was later incorporated into all radio proximity fuses. The electronic circuitry employed the principle of continuous wave transmission. The fuse transmitted a steady radio signal that bounced back from any nearby reflecting surface. The interaction between the outgoing and returning signals created an interference pattern that cycled through constructive and destructive phases as the shell approached its target. This cycling produced a small variation in the oscillator supply current that the receiver detected. When the amplitude of this variation reached a predetermined threshold, indicating the shell was close enough for its explosion to damage the target, a thyrotron trigger released an electrical charge stored in a capacitor. The thyrotron was a gas-filled tube that functioned like an electronic switch, capable of releasing the stored charge in a fraction of a millisecond. This charge tripped an electrical detonator that in turn set off the main explosive filling. Safety features prevented accidental detonation during handling, storage, and the moments immediately after firing. The centrifugal force from the spinning shell was required to arm the fuse by intentionally misaligning the triggering components until they were spun into proper position. This meant the fuse could not function until after the shell had left the gun barrel and achieved its full rotational speed. Additional time delay mechanisms ensured the fuse would not activate too close to friendly forces, typically requiring the shell to travel several hundred meters before becoming fully armed. By spring 1942, the project had grown beyond the capacity of the Carnegie Institution. Tuve approached the trustees of Johns Hopkins University to sponsor what he called the Applied Physics Laboratory. The trustees agreed despite being told virtually nothing about the laboratory's $1 million military contract. On March 10, 1942, APL was officially established in a former automobile garage and Social Security Administration office building on Georgia Avenue in Silver Spring, Maryland. Tuve became its first director and would lead Section T throughout the war. Working conditions were Spartan and the hours grueling, but Tuve drove his team with relentless determination. He posted dictums on the laboratory walls that became famous among the staff. One read, "I don't want any damn fool in this laboratory to save money. I only want him to save time." Another declared, "Shoot at an 80% job. We can't afford perfection. Don't try for an A. In a war, D is necessary and enough, but an F is fatal." A third stated, "The best job in the world is a total failure if it is too late." Perhaps most importantly, Tuve reminded his team, "Our moral responsibility goes all the way to the final battle use of this unit. Its failure there is our failure, regardless of who is technically responsible for the causes of failure." These words captured the urgency that drove the proximity fuse program. On August 12, 1942, the light cruiser USS Cleveland conducted live fire tests against radio-controlled drone aircraft over Chesapeake Bay, under the supervision of the Navy's Bureau of Ordnance. The T3 fuse had achieved a 52% success rate against water targets in testing on January 29, 1942 at Dahlgren, Virginia, and the Navy had accepted this performance as sufficient for combat use. The Cleveland tests exceeded all expectations. Gun crews brought down 3 drones on the first day, with just 4 bursts of proximity-fused shells. Despite evasive maneuvering by the drone controllers, the Navy immediately cancelled the remaining scheduled tests. There was no need for further proof. Mass production began within weeks. Contracts went to Crosley, RCA, Eastman Kodak, General Electric, McQuay Norris, Sylvania, and dozens of other companies. Each fuse required the assembly of approximately 130 miniaturized electronic components, including 5 of Van Allen's ruggedized vacuum tubes. A total of 87 different firms, using 110 factories, were eventually engaged in some phase of production work, with over 2,000 suppliers and subcontractors supporting the effort. Production began slowly, with factories assembling only about 500 fuses per day by the end of 1942. The complexity of the components and the need for absolute reliability limited how quickly production could ramp up. But American industrial capacity soon demonstrated its awesome power. By late 1944, production had reached 40,000 fuses per day. By war's end, over 70,000 fuses rolled off assembly lines every day from 5 major plants. The cost per fuse fell dramatically as production increased, from $732 in 1942 to just $18 by 1945. A total of 22,073,481 proximity fuses were manufactured by August 14, 1945, at a total cost exceeding $1 billion in contemporary terms, equivalent to approximately $15 billion today. This represented one of the largest military procurement programs of the war, outside of aircraft, ships, and the atomic bomb. The fuse received its baptism of fire on January 5, 1943, when the cruiser USS Helena engaged Japanese aircraft off Guadalcanal. 4. Aichi D-3, a dive bombers, known to the Allies by the codename Val, attacked a Navy task force in the early morning hours near Cape Hunter on the south coast of the island. One scored a hit on the New Zealand cruiser Achilles before the Japanese broke off their attack. As the surviving bombers departed, Lieutenant Red Cochran, commanding Helena's aft 5-inch battery, ordered a cursory barrage at the retreating enemy. 2 salvos brought down one of the Vals without scoring a direct hit. At least one shell had passed close enough to the dive bomber that the proximity fuse detected the reflected signal and detonated, shredding the aircraft with shrapnel from a distance of approximately 70 feet. Though it received no public attention at the time, the engagement marked a transformative moment in the history of artillery and aerial warfare. It was the first time in history that an enemy aircraft had been deliberately destroyed by a near miss. The combat success vindicated years of research and development and proved that the impossible had been achieved. The Navy jealously guarded its new weapon, restricting its use to engagements over open water where unexploded duds would sink beyond recovery. The fear of German or Japanese scientists reverse engineering a captured fuse and developing countermeasures, or using the technology against Allied bombers, was ever present. When a dud shell landed on Sicily during the invasion of July 1943, headquarters immediately dispatched a special patrol to find and retrieve it before the enemy could examine it. The Pentagon refused to authorize the use of proximity fuses over land, despite urgent requests from commanders who recognized the weapon's devastating potential against ground targets. This restriction frustrated many field commanders, but reflected the genuine importance attached to maintaining secrecy. This policy changed dramatically when the V-1 offensive began in June 1944. The flying bomb threat demanded immediate action regardless of security concerns. On June 12, 1944, one day before the first V-1 struck London, American authorities authorized the use of proximity fuses for the defense of Britain against the terror weapons. The coastal gun belt presented an ideal deployment scenario. Anti-aircraft batteries along the English Channel could engage incoming missiles over water, and any duds that fell into the sea would be lost forever beyond enemy reach. There was minimal risk of the enemy recovering an intact fuse for analysis. SCR-584 radars developed by the MIT Radiation Laboratory were rushed to England along with thousands of proximity-fused shells. The SCR-584, short for Set Complete Radio Number 584, represented the most advanced gun-laying radar of its era. Development had begun in 1940 at the newly established Radiation Laboratory, familiarly known as the RAD Lab, under the direction of physicist Luis Alvarez. The project, built on British cavity magnetron technology, delivered by the Tizard mission to create a system capable of automatic target tracking. The SCR-584 operated in the S-band at frequencies between 2,700 and 2,900 MHz using a 10 cm wavelength. Its 6-foot parabolic antenna could detect aircraft at distances up to 64 kilometers and track them automatically with an accuracy of approximately 20 meters in range and 0.06 degrees in angle. The radar employed conical scanning, in which the antenna beam rotated around its axis to determine the precise direction to the target. A plan position indicator display showed the overall tactical situation during search mode, while automatic tracking engaged and followed individual targets once acquired. The entire system was mounted on a single trailer weighing approximately 15 tons and could be set up for operation by a crew of 9 in under 30 minutes. The M9 gun director, developed by Bell Telephone Laboratories, processed the radar data through an analog computer that continuously calculated trigonometric firing solutions. Development had begun in 1940 under Warren Weaver of the National Defense Research Committee, with the initial design work completed by David Parkinson and Clarence Lovell under the direction of Edward Wente. A prototype designated T-10 was delivered to the Army only days after the attack on Pearl Harbor. The production model was paired with the SCR-584 as development of both systems continued in parallel. The M9 calculated course and speed of incoming targets, shell velocity and flight time, powder temperatures affecting muzzle velocity, shell drift from wind, air density variations with altitude, and dozens of other variables that affected where a shell would arrive and when. The system had 4 sets of outputs, allowing a single M9 to control 4 90mm guns simultaneously. Direction and range information from the radar was sent directly to the gun data computer, which pointed and elevated the weapons automatically without manual intervention from the crews. All the gunners had to do was keep loading and firing. When combined with proximity-fused ammunition, this system created the most effective anti-aircraft defense ever devised. General Sir Frederick Pyle commanded British Anti-Aircraft Command throughout the war, the only British general to hold the same command from beginning to end. Born in Dublin on September 14, 1884, Pyle had joined the Royal Artillery in 1904 and served with distinction on the Western Front during the First World War, earning the Military Cross and Distinguished Service Order. In the interwar years, he had been a pioneer in military mechanization, commanding the first experimental mechanized force and serving as Assistant Director of Mechanization at the War Office. He took command of anti-aircraft forces in 1939 and would guide them through every phase of the air defence of Britain. Working with Air Marshal Sir Roderick Hill of Air Defence of Great Britain, Pyle reorganised the defences against the V-1 threat. The original deployment placed gun batteries on the North Downs between the coast and London, with fighters patrolling ahead of and behind the gun belt. This arrangement created dangerous situations where fighters pursued V-1s second into the gun engagement zone, forcing batteries to hold their fire, while pilots risked being hit by friendly shells. On some occasions, fighters and guns engaged the same target simultaneously with tragic results. In mid-July 1944, Pyle ordered a massive redeployment that transformed the entire defensive system. Within days, the guns moved from the North Downs to a new coastal strip stretching along the shores of Kent and Sussex. This arrangement gave batteries clear fields of fire over the English Channel while keeping fighters well separated from the anti-aircraft zones. Fighters would engage V-1s second over the Channel and then break off before the missiles entered the gun belt. Any flying bombs that survived the coastal guns would face a final line of barrage balloons protecting the approaches to London. The relocation involved moving over 1,000 heavy guns and their associated radars, predictors, and fire control equipment, along with all necessary ammunition and support equipment. This massive logistical undertaking was accomplished in just 4 days, a testament to the skill and determination of anti-aircraft command. When the weather allowed both guns and fighters to operate, the fighters patrolled in front of the gun belt and only flew into the engagement zone when chasing individual V-1s second that had slipped through. The guns inside the coastal belt could fire with impunity up to 8,000 feet, provided no friendly aircraft were in the vicinity. The results of combining the new technology with improved tactics were immediate and dramatic. During the first week that proximity-fused shells and SCR-584 radars operated together in the coastal gun belt, 17% of all V-1s second entering the engagement zone were destroyed by gunfire. This represented a significant improvement over previous performance, but still left the majority of flying bombs reaching their targets. Week by week, performance improved as crews gained experience with the new equipment and refined their techniques. By the third week of August, gun batteries were destroying 60% of all V-1s second that entered the coastal strip. During the final week of the month, the destruction rate reached 74%, with one extraordinary day seeing 82% of incoming missiles shot down by gunfire alone. The transformation in ammunition efficiency was equally remarkable. At the beginning of the V-1 campaign, batteries expended an average of 2,500 shells for every flying bomb destroyed. With proximity fuses and radar fire control, this figure dropped to approximately 100 shells per kill. The guns had become 25 times more effective virtually overnight. As General Pyle later wrote, it was the proximity fuse which made possible the 100% successes. By the end of the fourth week of proximity fuse employment, the overall destruction rate reached 79% of all V-1s second entering the gun belt. The proximity fuse had saved London. The final day of major V-1 launches from ground sites in France demonstrated the system's effectiveness in stark terms. Radar detected 104 flying bombs approaching the English coast. Gun batteries equipped with proximity fuses destroyed 68 of them over the Channel. Of the remainder that made it past the guns, fighters and balloons accounted for most. Only 4 V-1s second reached London that day. The terror weapon that had seemed unstoppable just weeks earlier had been decisively defeated by American technology and British determination. The V-1 campaign from fixed launch sites in France ended in early September 1944 as Allied forces overran the launching areas around the Pas de Calais. But Germany was not finished with its vengeance campaign. The Luftwaffe adapted Heinkel He 111 H-22 bombers to carry V-1s second under their wings, allowing launches from over the North Sea beyond the range of the existing gun belt. This method allowed V-1s second to flank the established coastal defences by approaching from the northeast rather than the south. New defensive positions were established along the coast of East Anglia and later along the Lincolnshire-Yorkshire coast to counter these threats. Meanwhile, Germany redirected its flying bomb offensive against the vital port of Antwerp, through which Allied supplies flowed to sustain the advance into Germany. The British 11th Armoured Division had captured the port on September 4, 1944. Over the following months, German forces launched thousands of V-1 flying bombs and V-2 ballistic missiles against the crucial logistical hub in an effort to destroy the port facilities and disrupt Allied supply lines. The defence of Antwerp presented new challenges. When Germans adjusted their V-1s second to fly at altitudes as low as 1,200 feet, the lower trajectories made interception vastly more difficult. The existing fuses had been optimized for targets at higher altitudes. Scientists at the Applied Physics Laboratory quickly designed modified fuses for the 3.7-inch and 90mm shells needed to engage targets at such heights. Production was rushed at the Crosley factory in Cincinnati, Ohio. British Prime Minister Winston Churchill authorized a special flight of Lancaster bombers to transport the modified fuses directly from Cincinnati to Antwerp, a measure of the desperate urgency attached to defending the crucial port. The Antwerp defences ultimately achieved remarkable success. Additional radar units and observers were deployed up to 64 kilometres from the port to provide early warning of approaching missiles. The combination of proximity fuses, radar fire control, and experienced gun crews resulted in destruction rates approaching 80% of incoming V-1s second. The anti-aircraft defences prevented the overwhelming majority of flying bombs from reaching their targets, protecting the vital port facilities that sustained the Allied advance into Germany. The proximity fuse proved equally valuable in applications beyond air defence that emerged in the final months of the war. In December 1944, German forces launched their last great offensive in the west, striking through the Ardennes forest in what became known as the Battle of the Bulge. On the morning of December 16th, Colonel George Axelson of the 406th Artillery Group faced a difficult decision. German forces had just attacked the 38th Cavalry Squadron dug in around Monschau, and the lightly armed cavalrymen desperately needed fire support. Axelson had recently received a new type of artillery shell equipped with proximity fuses, but General Eisenhower had not yet given formal permission for their use over land. The colonel decided the emergency trumped the restrictions and ordered his gunners to open fire with the new ammunition. Minutes later, shells began exploding directly over the heads of attacking German infantry. The effect was devastating. When a proximity-fused shell detonated at the optimal height above ground, typically 6 to 15 meters or 20 to 50 feet, it showered the area below with shrapnel that no foxhole or trench could protect against. Soldiers who would have survived a conventional shell exploding in the mud found no shelter from explosions that occurred above them. German prisoners described the attacks as quick, powerful bursts for which there was simply no defense. One prisoner from the 8th Infantry Division sector in the Hürtgen Forest said simply that the shells were like nothing they had experienced before. General George Patton later wrote to the War Department, "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell we will have to devise some new method of warfare. I am glad that you all thought of it first." Patton credited the proximity fuse with significant contribution to victory in the Ardennes, though many factors contributed to the German defeat. The weapon proved equally effective in the Pacific theater against Japanese kamikaze attacks. When waves of suicide aircraft bore down on American warships off Okinawa and elsewhere in the final year of the war, proximity-fused shells created a wall of exploding steel that few could penetrate. Admiral Arleigh Burke, who later became Chief of Naval Operations, recalled, "When I went as Chief of Staff to Vice Admiral Mitscher, who commanded the fast carrier task forces, all the 5-inch 38 and 5-inch 25 ammunition was fitted with VT fuses, and as you well know, those fuses knocked down enemy planes by the dozens. One analysis of combat records estimated that 278 aircraft were destroyed by proximity fuses between October 1944 and August 1945. Using conventional time-fused ammunition, only 46 of these would likely have been destroyed. Navy studies found that while time-fused 5-inch guns required approximately 1,000 shells to destroy an aircraft, proximity-fused ammunition needed only about 250 shells to achieve the same result. The fuse was credited with 50% of all enemy aircraft destroyed by shipboard anti-aircraft fire, despite representing only 25% of ammunition expended. Secretary of the Navy James Forrestal summarized the weapon's impact. "The proximity fuse has helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater." Speaking specifically about the V-1 campaign, Prime Minister Winston Churchill stated, "These so-called proximity fuses made in the United States proved potent against the small, unmanned aircraft with which we were assailed in 1944. The proximity fuse remained one of the most closely guarded secrets of the war until its existence was revealed in September 1945 after Japan's surrender. The secrecy had been maintained so effectively that even the soldiers and sailors who used the weapon often did not understand why it worked so well. German and Japanese forces never developed effective countermeasures because they never fully understood what they were facing. Post-war investigations revealed that while Germany had pursued more than 30 different proximity fuse designs for anti-aircraft use, perhaps as many as 50, none had achieved operational status. German scientists understood the theoretical possibilities, but lacked the industrial capacity and miniaturization technology to produce working fuses in quantity. The legacy of the proximity fuse extended far beyond the battlefields of the Second World War. The miniaturization techniques developed for the ruggedized vacuum tubes provided a foundation for post-war electronics development that would eventually lead to the transistor and integrated circuit. When James Van Allen designed scientific instruments for America's first satellites in the late 1950s, he drew directly on the knowledge gained from proximity fuse research. The same principles that allowed electronic components to survive being fired from a cannon enabled them to endure the extreme vibration and acceleration of rocket launch. Van Allen's instruments aboard Explorer 1 in January 1958 discovered the radiation belts surrounding Earth that now bear his name, a direct intellectual descendant of wartime fuse development. The Applied Physics Laboratory, born from the desperate need for a weapon to defend ships from air attack, grew into one of America's premier research institutions. From its wartime staff of 800, APL expanded to employ thousands of scientists and engineers working on advanced defense technologies. The laboratory developed surface-to-air missiles, submarine warfare systems, and spacecraft that have explored the outer reaches of the solar system. Today, APL continues to address national security and scientific challenges with technical expertise rooted in its wartime origins, a direct descendant of Section T, and Merle Tuve's determination that the best job in the world is a total failure if it is too late. In the summer of 1944, London faced annihilation from weapons that seemed impossible to stop. The V-1 flying bomb exploited every weakness of conventional anti-aircraft defense, its small size and tremendous speed making it nearly invulnerable to the guns and fighters of the era. Within 4 weeks of deploying the proximity fuse, British and American forces transformed a desperate defensive struggle into a decisive victory. The invisible burst that detonated without touching its target saved thousands of lives and demonstrated that scientific innovation could overcome seemingly insurmountable military challenges. The proximity fuse stands as a testament to what can be achieved when brilliant minds are given the resources and freedom to solve impossible problems. From Merle Tuve's laboratory at the Carnegie Institution to the factories that produced over 22 million fuses, from James Van Allen's work on ruggedized vacuum tubes to the gun batteries that shattered Hitler's vengeance weapons over the English Channel, the proximity fuse represents one of the greatest technological achievements of the 20th century. Its deployment changed the nature of aerial warfare forever, and its success in the summer of 1944 proved that even Hitler's wonder weapons could be defeated by the ingenuity and determination of free peoples working together toward victory.